Before we start, another announcement about the coding practice. You have to get everything accepted within 3 days now, and most people have done it. Don't get an F for no reason, please. Okay. And by the way, if you said in the form that you want to be contacted by us, one of the TAs will write to you very soon. Okay. So we're still talking about graph traversals. We talked about DFS and DFS. We saw how to solve a bunch of different problems using DFS and BFS. And the last problem we saw in the last session was the problem of strongly connected components. So if I have a directed graph G, I say that two vertices U and V are in the same strongly connected component if there is a path from U to V and a path from V to U. So I should be able to reach each one of them from the other one. And being in the same strongly connected component is, of course, an equivalence relation. So it divides all of our vertices into several different components. We call them strongly connected components, SCCs. And we saw an example towards the end of last session. So if I have this particular graph, you can see that 1 and 2 are in the same strongly connected component because you can reach each one of them from the other one. You can also see that since I have this cycle here, all these 4 vertices should be in the same strongly connected component. And similarly, these 3 vertices were their own component, and then each one of these 2 vertices forms a component with only 1 vertex. Now, the question at the end of last session was, how would I actually calculate or compute all of the strongly connected components of a given graph? And the idea we saw was that I can take just one cycle and I can say all the vertices in this cycle are definitely going to be in the same component. So let's merge them all into just one vertex. Okay. And then the algorithm was very simple. I just keep finding cycles and merging the vertices in that particular cycle into just one vertex. And I do this until I get a DAG, until I get to a directed graph that has no more cycles. And then every vertex in that DAG will correspond to one of the strongly connected components of my original graph. But this is not very efficient, right? So finding cycles, I mean, we know how to find cycles using DFS. I can just do one DFS. And if I see a back edge, that's a cycle. And then I can merge everything in that cycle, but I might have to do this many times. Imagine if my graph has a ton of triangles, a lot of cycles of length 3. Then I would have to constantly do a DFS to find the cycle and then merge it, and then again do another DFS to find the cycle and merge every vertex in it into one vertex and so on. So it's actually easy to do it in O n squared plus nm. And this is basically just finding cycles over and over again and doing one DFS for every cycle finding. So I'm doing at most n DFSs here. But I want to do it with one DFS. Okay. So let's just take this same graph and let's do a DFS. And let's see what we get. I'm going to take this graph and let's put it here. And let's say I'm just going to choose some vertex and do a DFS from that vertex. I'm choosing a vertex arbitrarily here. So let's say I choose vertex 6. So I'm doing DFS from 6. Okay. Let's do the DFS. I put 6 as the root of my DFS tree. And then let's say from 6, I can go to 8. So I would add maybe 8 as its child. And then from 8, I can go to 11. From 11, I cannot go anywhere else. I go back to 8. Again, I cannot go anywhere else. I go back to 6. I see that I can go to 7. From 7, I can go to 8, but I have already seen that. I can go to 9. And from 9, I can go to 10. From 10, there is really nothing I can do. Actually, if I want to just draw my path here, from 6, I went to 8. And then from 8 to 11, then I went back. Then I went to 7. Then from 7 to 9, and then to 10. So now I go all the way back to 6, and I see that I can go to 5 as well. Okay, so I would add 5 as a child of 6. And now from 5, I can go to 3 to 4. So I can go something like this. So I would just add 3 as a child here, and 4 as a child here. I can't really go anywhere from 4. I mean, I can go back to 6, but I've already seen that. I go back to 3. I mean, I can take this edge, but it doesn't really help me at all. There's nowhere else I can go. So this is my DFS tree if I do a DFS from vertex 6, right? And of course, it's not going to always contain all of my vertices, because it will only contain the vertices that are reachable from 6, right? And in this particular graph, everything was reachable from 6 except for 1 and 2. So at this point, I already know for sure that 1 and 2 are not in the same strongly connected component as 6, because I did a DFS from 6 and I saw that I cannot reach 1 and 2, right? But it doesn't mean that everything else that I have seen is just one strongly connected component. Actually, as we know here, we have several different strongly connected components here. These are all the vertices that are reachable from 6, but it doesn't mean that they can all also reach 6, right? But let's continue with creating our DFS forest. So I find another node that I have not seen before, for example, 2. And I do a DFS from 2. And in this case, it's just going to give me this. It's a very simple thing, right? So I start from 2, I go here. Okay, so this is my DFS forest. Now I can look at all of the edges of my original graph and see what they do in my forest. So for example, I have an edge from 1 to 2. Right? So this is a back edge in my forest. What does the existence of this back edge tell me? What can I conclude here? I can conclude that 1 and 2 are in the same strongly connected components, right? Generally speaking, whenever I have a back edge, it's always going to create a cycle, because in my DFS tree, I can always start at the top and go down. And then the back edge lets me go back up. So that creates a cycle. So here, because I see this cycle, because I see this back edge from 1 to 2, I already know that 1 and 2 are going to be in one strongly connected component. Okay, but let's look at my other edges. So I have an edge from 1 to 3. Now, this is a cross edge, and it's a cross edge like this. It's going from one of my trees to another tree. Right? Would this give me any new information about my strongly connected components? No, because here's the thing. The fact that I have a cross edge like this means that it would have been impossible to go from 3 to 1, right? Because when I did my DFS, I reached 3 first in my first tree, right? So if 1 were to be reachable from 3, I would already find it in the same tree. But I didn't find it in the same tree. That's why 1 is in the second tree. And so this edge, it doesn't mean anything. It's not going to create a new strongly connected component for me. In other words, if I have 2 vertices that are in 2 different trees of my DFS forest, I'm definitely sure that they're not in the same strongly connected component, right? So I can pretty much ignore this edge. Like, who cares about this edge? It's not changing my strongly connected components. And I can say the same thing about the edge from 1 to 4. So again, I have an edge from 1 to 4, but I'm sure that there is no way to reach 1 if I start at 4. So they're not going to be in the same strongly connected components. Okay, what other edges do we have? Well, I have a self loop here from 3 to 3, but that's like the most useless kind of edge, of course. It's not going to affect anything. I have this edge from 4 to 6. Okay. Now, the edge from 4 to 6, if I look at it in my DFS tree, it's an edge like this. It's a back edge. So it's going to create a cycle, which means that all of the vertices in this cycle are going to be in the same strongly connected component. Now, what are the vertices in this cycle? 4, 3, 5, and 6. So I already found this strongly connected component, right? I found out that all of these vertices are going to be in the same strongly connected component. Okay. But how do I make this systematic? Well, I can say I first do my DFS. I create my DFS first, and then I keep going over my edges. And in this case, as soon as I saw an edge like this, I know exactly which vertices I have to collapse into one vertex, right? So in this case, I would just merge all of these vertices 4, 3, 5, and 6 into one vertex, because I know that they're in the same strongly connected components. Okay. Let's continue with this. I have an edge from 6 to 3. 6 to 3 is an edge like this. It's a forward edge. Now, forward edges are also not going to give us any new information. Because, look, this vertex was already a descendant of this one, which means that in my tree, I already had a path that started at 6 and ended at 3. So the fact that now I have a direct edge, that's not going to change the connectivity. I could go there anywhere. So I don't need this. I can just ignore this edge. So as you see, I'm pretty much ignoring the cross edges that went between different trees. And I'm also ignoring the forward edges because they don't really affect my strongly connected components. But whenever I have a back edge, I'm merging all of the nodes that were in the cycle created by that back edge. But we can also have cross edges in the same tree, right? What happens if I have that? Let's just continue with this example. I hope I find one of those. So we did 6 to 3. We have 5 to 4. 5 to 4 is also a forward edge. I don't care about this. We have 5 to 7. Nice. This is a cross edge, right? And this is a cross edge between two vertices of the same tree. Now, what does this tell you? It tells you that if I start at 5, I can go to 7, of course, because I can just take this one edge. Okay, so now I have this edge from 5 to 7, and this is a cross edge. So you might think that I can just ignore it like the cross edges that went between different trees, because I can pretty much make the same argument, right? I can say that from 5, I can reach 7, but from 7, I couldn't have reached 5 because otherwise 5 would be in the subtree of 7. But actually, this is not the case, because imagine if the subtree of 7 has a back edge that goes above 7. So for example, imagine if I had an edge from 10 going all the way to 6, right? So that would be a back edge like this that goes from 10 to 6. And now this cross edge from 5 to 7 actually matters, because I can go from 5 to 7, I can go down the tree to 10, and then I can take the back edge back to 6. And of course, because from 6 I could go to 5, this creates a cycle. So it means that all of them would be in the same strongly connected components. Now, I'm going to remove this edge, but I just wanted to say, make sure that you distinguish between the edges, between the cross edges that go between different trees and those cross edges that go in the same tree. The cross edges that go in the same tree can actually matter for the strongly connected components. So that's it. That's my algorithm now. And it's a very simple algorithm, right? Just do a DFS, you get a DFS forest. and then go over all of the edges of your graph. Whenever you see a cross edge, ignore it. It's not going to change your strongly connected components. Whenever you see a forward edge, ignore that as well. It's not changing anything. Just when you see a back edge, for example, you had this back edge from 4 to 6, you just merge all of the vertices in this cycle. So you merge 4, 3, 5, and 6. Okay, that's all you have to do. Okay. So now I found a way of basically finding all of my cycles and merging all of them with just one DFS instead of doing a separate DFS to find each cycle. But what is my runtime right now? Well, I have a tiny bit of a problem here. And my problem is that how do I know if a particular edge is a back edge? Right? So I can do my DFS in ON plus M, and I do it. It gives me the DFS forests. I'm happy with that. Now I'm going to go over all of my edges here, and I have to somehow know, is this edge a back edge or not? Right? Now, you can use a lot of really interesting data structures for that, and we're going to see some of the really nice things for finding like the lowest common ancestor and things like that. But the answer here is that instead of finding the back edges later, let's just find the back edges as we are doing our DFS. Okay. And usually the way people present this is using a color scheme. So the idea is this. Let's say I'm doing a DFS. I'm going to color my vertices with 3 colors. I'm going to have white, gray, and black vertices. Okay. So this is the idea. Do a DFS, but have 3 colors for vertices at any given time. And the colors of vertices can change. Okay. So I'm going to have white vertices, and these are the vertices that I have not seen in my DFS yet. Okay. So white means it's not seen. I'm going to have gray vertices, and gray means that I have seen it, but right now I'm just exploring its descendants. Okay. So I have seen this vertex, but I'm not completely finished with it. It's possible that I come back to this vertex and try to explore a different path from this vertex. Okay. Seen, let's say, but not finished. And finally, I'm going to have black vertices. And these are the ones that I'm absolutely done with. So I've seen this vertex. I've seen everything that was reachable from this vertex. I'm never going to touch this vertex in my DFS ever again. Okay, so this is completely finished. Okay, so here's the thing. Let's do this DFS with these colors again. Do I have it here still? Yes, okay. So let's say I do a DFS from vertex 6. Okay, so originally my vertex 6 would be gray because I've seen it, and I've started my DFS from 6, right? Now from 6, last time, let's do the same as last time. So I went to 8. So this means that in my DFS tree, I will have 6, which is gray, and then I'm going to go to 8, and 8 also becomes gray. And everything else is white at this point. Now from 8, I go to 11. Because I see 11, 11 also becomes gray. Now from 11, I realize that there is nowhere else I can go. So I want to go back to 8. But whenever I'm going back to the parent, I'm going to just color this black, because I know that I'm done with 11. So 11 becomes black. I go back to 8. Now from 8, I cannot go anywhere else. So 8 also becomes black, and I go back to 6. 6 is still the same color as before. It's gray. So I go to 7. Okay, 7 becomes gray, and so on. And I just continue this. So you understand the coloring. But other than keeping track of these colors, as I'm doing my DFS, I'm also going to see all of the edges anyway. Remember, whenever I go to a vertex, I'm going to try all the edges that go out. But in my DFS, I said that if an edge goes to a vertex that I have seen before, if it goes to a gray or a black vertex, I will not go back to it, right? That was the idea. But now let's see. Let's see what happens here if I look at these edges. So I'm at 7, 7 is gray. I go to 9, right? So 9 becomes gray as well. Then from 9, I go to 10. 10 becomes gray as well. Okay. Now, from 10, I have an edge to 7, right? But at this point, I know that I have seen 7 before, so I know that this edge is definitely not going to go into my DFS tree. But my question is this a back edge? How can I know if this edge that I'm just seeing, but I'm sure I'm not putting in my tree, how can I know if it's a back edge? Well, it's a back edge if it's going to a gray node, right? Because I just got to vertex 10, and I'm seeing an edge to vertex 7. What are the nodes that are gray right now? They're exactly the ancestors of 10, right? So whenever I see this edge, I already know the color of the other side. I ask, is the other side gray? And if it is gray, I found a back edge. So I realized that this edge from 10 to 7 is a back edge. And I said that whenever we have a back edge, we would just merge all of the vertices between these two into just one strongly connected component. So now I know that because I have this back edge, 7, 9, and 10 are in the same strongly connected component. So I found this strongly connected component. I merged all of them together. Okay. And now I continue with my DFS. So from 10, I go back to 9, and 10 becomes black now. Then from 9, I go back to 7. 9 is now black. Now I'm at 7. From 7, I see that I can go to 8, right? So again, the question is, I have this edge from 7 to 8. 8 is already seen in my DFS. So I'm not going to put this edge into my DFS tree. But is this a back edge? And now the answer is no, because 8 is already black. So 8 is not one of the ancestors of 7. Now I continue with my DFS. So 7 becomes black. I go back to 6. From 6, I see that I can go to 5. So I see 5. 5 becomes gray. I have 5. Okay. And then from 5, I can go to 4, or I can go to 3, whatever. Let's say I go to 3 this time, or actually, which one is better? Should I go to 4? Yeah, let's say from 5, I can go to 4. So I go to 4, 4 becomes gray. From 4, I see that I can go to 6, right? But 6 is already gray. So this means that the edge that I'm seeing from 4 to 6, it's a back edge. So I have to merge all of these vertices. I have to merge all the vertices between 4 and 6, 4, 5, and 6. And I do it. I merge all of them, and I say all of these are definitely in the same strongly connected components. Okay? But very importantly, this doesn't mean that this is the entirety of my strongly connected component. I just know at this point that these 3 vertices are going to be in the same strongly connected component. But maybe that component also includes some other vertices. So I'm going to continue with my DFS. So from 4, I see that I can go to 6. I merge them. Now from 4, I cannot go anywhere else. So 4 becomes black. I make it black. I go back to 5. From 5, I can go to 3. So now 3 becomes gray, and it also becomes a child of 5. Now from 3, again, I see that I have an edge to 6, right? No, I don't. Oh, sorry. Yeah, I don't. From 3, sorry, I see that I have an edge to 4. I thought this edge was in the other direction. But 4 is already black, isn't it? No, 4 is actually gray, because remember, I merged all of these into the same vertex. So 4, 5, and 6 are now the same vertex for me. And even if one of them is gray, all of them are gray. Okay. So this edge from 3 to 4 is actually considered a back edge because, okay, basically the way I want you to think of this is let's go back to what happened when I was at 4. When I was at 4, I saw that there is an edge to 6, and 6 was gray. So I said that this is a back edge. So I want to merge 4, 5, and 6. So I merge all of them, and I now think of all of them as just one vertex, right? So you can imagine it like this. Now I have just one vertex, which is all of them. It's 4, 5, and 6, and it's gray. Okay, but I continue with my DFS. So continuing with my DFS, from 4, I went to 5. Now 4 becomes black, but this one becomes black only when everything in it becomes black. So from 5, I could go to 3, which means that from this vertex, I could go to 3. And 3 becomes gray. Now from 3, I see that there is an edge to 4, but now that's a back edge, right? Because 4 is now part of this whole vertex that corresponds to all of them. So I would again merge all of these into one vertex. So now finally, I, at this point, found my strongly connected component. Now, of course, I have to continue with my DFS because I haven't seen vertices 1 and 2. And like my DFS ends here, like after this point, I will just make everything black because my DFS tries to find new vertices, but it cannot find any new vertices. Everything goes black. I haven't seen all of my vertices, so I have to continue my DFS from an unseen vertex. And, oh, actually, I forgot. There is also this 8 and 11. So no. Yeah, this DFS is going to continue. It's going to continue, and I'm going to see 8. No, I had 8 and 11. What am I doing? No. Okay, 8 and 11 are already there. That's fine. I've seen all of them. I continue the DFS and I see 1 and 2. So I'm going to have, let's say this time I do my DFS from 1. Then I go to 2. Then I see that there is an edge from 2 to 1. So that's a back edge. So I merge them into the same strongly connected component. And that's it. So these are my strongly connected components. And the vertices that are not merged with anything, they're just a strongly connected component on their own. Okay. But this is now finally just one DFS. So I have a runtime of ON plus M. But it's a little bit hard to implement, right? So can I implement it in an easier way? Instead of doing all of these mergers, could I, for example, just use my DFS trees to just identify all of my strongly connected components in an easier way? So here's the thing. These are my strongly connected components, and this is my DFS tree. So let me just copy this one. And by the way, our DFS forests are not unique. So based on which order you use in visiting, you can get different trees. Okay, let me erase this part. Okay, look at this. I have my graph and I have my strongly connected components. And on this other side, I have the trees that were created by my DFS. So let's just look at my strongly connected components in these trees. I have 1 and 2, so this is one of my strongly connected components. I have 3, 4, 5, and 6, right? So this is another one of my strongly connected components. I have 8, I have 11, so this and this, and I have 7, 9, and 10. Interesting. So if I look at each one of my strongly connected components in my DFS trees, they're also connected in the DFS tree, right? But that's quite easy to figure out because that's basically how I was finding all of my strongly connected components. I was just saying, find a package. But if I have a package from U to V, there was already a path from V to U, right? So I can pretty much identify each one of my strongly connected components just with its highest vertex in my DFS tree, right? So I would call this one 2. I would just say this is the strongly connected component of vertex 2, right? And this one, I would say this is the strongly connected component of vertex 6. So I just take one of the vertices as the representative of the strongly connected component, and it's always the vertex that appears highest in my DFS tree, okay? So this is 8, this one is 11, this one is 7. Okay. Now, instead of just trying to find all the strongly connected components as before, I can do something different. I can say, let's look at these DFS trees and let's ask, if I take this particular vertex, for example, I take vertex 5, is it the representative of a strongly connected component? Is it the highest vertex of one of my strongly connected components? How can I know if a particular vertex is the highest vertex of a strongly connected component? Again, remember that my strongly connected components were created by my packages, right? So if I have this vertex here, and I have a package that goes from somewhere below it to somewhere above it, then everything in between will be in the same strongly connected component. So this vertex will not be the highest vertex of its strongly connected component. Actually, the end of the package is higher, right? So that's what I want to check. Basically, I want to check for each one of these vertices, is there a package that crosses from somewhere below me to somewhere above me? That's what I want to answer. Okay, so here's what I can do. First of all, I can assign a depth to all of my vertices in the same way that we assign depths in all of our trees, so on. So this one is at depth 0. This one is also at depth 0. These are at depth 1. These ones are at depth 2. This is at depth 3. Okay. So I assign a depth first. Now, here's what I'm going to do. I'm going to do, well, dynamic programming. We will get to dynamic programming soon. But generally speaking, for every one of the vertices, I want to know if I look at all the packages that start in the descendants of this vertex, how high can they go? Okay. So I'm going to actually, let me just copy this whole thing one more time. By the way, good luck understanding this without watching the video. Okay. So here's what I'm going to do. For each one of my vertices, I want to calculate a value. I'm just going to give it any name. Let's call it A. So A of a vertex V is going to be the lowest level, or yeah, the smallest level reachable by a package in the subtree of V, in V's descendants. Okay, I'll show you what I mean on this example. Again, remember this is my DFS tree or the two DFS trees. I also know the levels of all the vertices. So these are vertices at level 0, level 1, level 2, level 3, and so on. I'm just going to go over all the edges of my graph, and I'm only going to care about the back edges. But I'm going to do it in the order that is bottom up based on my DFS trees. So here I'm going to start with vertex 4. I'm going to start at the bottom of my DFS tree. And I'm going to ask, what are the edges that go out of 4? 4 has an edge to 6, right? That's the only edge that is going out of 4. And it is a back edge. So it's a back edge to level 0. So I know that from vertex 4, I have a back edge to level 0. So I set the A value at 4 to 0. I'm just going to use a different color for this. Let's use blue. So the value here is 0. Now, let's say I want to calculate my A value for vertex 3. I look at all the edges that are going out of 3. I have 3 to 4, but that's not a back edge, right? How do I know that it's not a back edge? Again, this is pretty much the same as what I was doing here. So I'm doing it at the same time as my DFS. Or another way of looking at this is that when I was doing my DFS, I can also mark all of my edges. I can remember which ones were back edges, right? Okay. So I get to vertex 3. I look at all the back edges that go out of 3. There is no back edge from 3, right? But there was a back edge from one of its children, from 4, that went to level 0. So the answer for 3 is also 0. Basically, what I'm saying here is that if I look at all of the subtree of this vertex, and if I look at all of the back edges, how high can they go? That's what I'm calculating here. Okay. From 5, what is the highest back edge that I can have in this subtree? Again, it's the back edge that goes from 4 to 6, basically. So here, the answer would also be 0. And of course, at 6 itself, it would be 0 too. Now, let's do this. At vertex 10, I have an edge to 7, and it's a back edge. And 7 was at level 1. So from 10, I have a back edge to level 1. From 9, I don't have any back edges, but from its child, I had a back edge to level 1. So here I also say the highest level I can go is 1. From 7, I actually don't have any back edges, right? But from its child, I had level 1. So I say here the answer is also 1. Now, from 11, I have no back edges at all. I have no edges coming out of 11. So I can only reach the same level as 11, which is level 2. So I have to stay at level 2 if I start at 11. From 8, I can go to 11, or I can just stay at 8. So here the answer is 1. So generally, this value, this blue value that I'm calculating here, is again the smallest level, the highest level that I can reach by back edges in the subtree of the current node. Okay, so now here I have computed all these A values for all of the vertices. So again, remember that the A value tells you how far up you can go using back edges. So if I just compare the A values with the depths of these vertices, I can already rule out some vertices as representatives of strongly connected components. For example, look at vertex 4 here. Vertex 4 is at depth 3, but it has an A value of 0. So it means that using the back edges, I could start at vertex 4 and reach something at level 0. So vertex 4 cannot possibly be the highest vertex in its own strongly connected component, because of course it can reach something at level 0, and then that thing at level 0 can also reach vertex 4 at level 3. So 4 is definitely not a representative. So I can say 4 is not a representative. Similarly here, you see whenever there's a mismatch between the depths and the A value, I can say this node is definitely not a representative. So 4 is not a representative, 10 is not a representative, 3 is not a representative, 9 is not a representative, 11 might be a representative, 5 is not a representative, 7 might be a representative, right? 8 might be a representative. 6 is definitely a representative because 6 is actually the root of the tree. So whenever you have a root, of course, this root is going to be the highest vertex in its own strongly connected component. So I'm sure that this one is definitely a representative. Now, 1 is not a representative because it has a back edge to 1 level above itself, and 2 is definitely a representative, right? So here's my situation. I have a bunch of vertices that I know are not representatives. And then I have these circled vertices, which may or may not be representatives. Now, can I say all of them are definitely representatives? All of them are the highest vertex in their own strongly connected component? Well, in this particular case, on this particular example, yes, they are actually each of them a representative. And you can verify this because vertex 8 is the only vertex in strongly connected components, the same for 11, and then the strongly connected component of 7 is just 7, 9, and 10, which are all below 7. But we were just lucky here. This doesn't happen in general. In general, you cannot say that if the A value is equal to the depths, then you're at a representative. Now, why is that? So let me try to create an example where this doesn't work. So remember that when we're looking at strongly connected components, we have to, of course, look at the tree edges and back edges were the main thing that created our strongly connected components. But we could not ignore the cross edges that were in the same tree. So here's what's going to happen. Suppose that in my original graph, I had an edge like this, right? And then suppose that I also, so this is a back edge. It shows that 6, 7, and 9 have to be in the same strongly connected component. Now, let's say that later on, I figured out that I also have a cross edge like this from 5 to 7. Now, I can go from 5 to 7, then take the path to 9, take that back edge, and then from there come back to 5, right? So you see, this is a combination of back edges and cross edges that are creating my cycle. I could have even weirder combinations. Maybe I have a combination like this. Maybe I have to take 2 cross edges, and then that allows me to take a back edge, right? But then I might have 2 cross edges, and I might have a back edge like this, but I cannot go back to 5 because the back edge doesn't go to any of the ancestors of 5. So you see, life is complicated in general. So here's another issue. Suppose that I had a cross edge like this, and then I have a back edge like this, right? And then let's say I also have this kind of back edge. So I have to take the cross edge, go down, take the back edge up, and then take the back edge again. Generally speaking, I can have any combination of cross edges and back edges. So this is not going to help me if I want to identify these representatives. So I have to think more formally about what a representative is. So here's my question. When is a vertex V a representative? This is the question I want to answer. Now, of course, the simple answer is to just look at the definition that we had for representative. And we said that V is a representative if it's the highest node of its own strongly connected component in our DFS tree. But that's not a good answer because I'm doing all of this in order to find the strongly connected component. So even though mathematically it makes sense to say that the representative is the highest vertex of the current strongly connected component, because I don't know what the strongly connected component is, I cannot find the vertex V like this. But let me see, what else can I say? I can also say V is a representative if V is the first vertex of its strongly connected component to be seen. Of its strongly connected component to be seen in my DFS. Right. Now, I still have the same problem. I still have the problem that I'm saying V is the first vertex of the strongly connected component that is seen in my DFS. I don't know what my strongly connected components are. Okay. So that's not good. What can I do? How can I find this out? Well, here's the idea by Tarjan. So Tarjan's idea, it's actually very simple, but also very elegant. It's that we keep track of a stack of vertices. So keep track of a stack of visited vertices. Basically, what are the vertices that my DFS has seen? Okay, and it's a stack because I'm only going to ever add to the end of this list and remove from the end of this list. So keep track of a stack of visited vertices. And then also color the vertices as you visit something. So let's say I visit a vertex. The first time I visited, I would color it gray and I would add it to the end of my stack. The important point is how you remove vertices from your stack. So the idea is that when you reach a vertex, if you have a path to somewhere earlier in the stack, if you have a path to, let's say, something to the left of the current vertex in the stack, then you know that the current vertex is not a representative. And if you don't, then you know that the current vertex is a representative. Now, if that doesn't make sense to you, let me just do an example. And then we'll actually prove that this works. Okay. So again, we have the exact same graph as before. And now I also have a stack. So I have this stack, which will keep track of all the elements. Or actually, let me put it on this side. So this is my stack. Let's say I start my DFS from vertex 1. So initially, I put 1 on my stack. And I'm putting 1 as the root of my DFS tree. And 1 is gray at this point, right? Because I've just seen 1. Now from 1, I see that I can go to 2. So I go to 2, I add 2 here, and 2 is also gray. Now, at this point, 2 becomes black, because from 2, I see that I cannot go to any new point. But what's interesting to me is to ask from 2, from this vertex 2, could I go to any of the vertices that were to the left of the vertex 2 in the stack? And the answer is yes. From 2, I could actually go to 1, and 1 is added to the stack before 2 was added. So 1 is to the left of 2. Now, if this is the case, if I can reach a vertex that was to the left of the current vertex on the stack, then I don't remove my current vertex from the stack. Otherwise, I will remove it. So now in this case, from 2, I could reach 1. 1 was before 2 on the stack, so I'm not going to remove 2 from the stack. 2 becomes black. I continue my DFS. I go to vertex 1. Now from vertex 1, I see that I can go to vertex 4. So I add 4 here as well. Now 4 is again gray at this point. From 4, I see that I can go to 6. So I go to 6. 6 is gray. I add 6 to my stack. From 6, I can go to 5. So I go to 5. 5 is gray. I add 5 to my stack. From 5, I see that I can go to 3. So I go to 3. And 3 is again gray and also added to my stack. Now from 3, I see that there is nowhere else I can go. Right, I've seen everything else that I could see. So at this point, I want to make 3 black. So I make 3 black. But I also realized that from vertex 3, I could go to vertex 4. And vertex 4 was before vertex 3 in the stack. So I could reach something to the left of myself on the stack. And for that reason, I'm not going to remove the vertex 3 from the stack. Okay, so 3 remains on the stack. I go back to 5. From 5, again, I see that I can reach 4, which is something that was before me in the stack. So 5 is also going to, oh, sorry, no, I just realized that from 5 I can go to 7. I haven't explored this part yet. So from 5, I go to 7, sorry, and 7 is now gray, and 7 is also added to the stack. From 7, I see that I can go to 9. So I go to 9. 9 also gets added to my stack. I'm writing my stack in 2 lines now. And then from 9, I see that I can go to 10. And 10 is also now gray and added to my stack. From 10, I see that I can go to 11. So 11 becomes gray and added to the stack. Now, here's the thing. At this point, from 11, I see that there is nowhere else I can go. So 11 is going to become black. But also from 11, I couldn't reach anything earlier on the stack. But here's the thing. I only pop something from my stack when that vertex becomes black, right? So when I'm at 11, I know that all of the ancestors of 11 are already on my stack. My stack might contain some extra elements, but all of the ancestors of 11 are definitely there. 1, 4, 6, 5, 7, 9, and 10. They're all here, right? So if I started at 11 and could not reach anything before 11 on the stack, it means that from 11, I cannot reach any of its ancestors. Now, let's look at it from the point of view of strongly connected components. If I look at it from the point of view of strongly connected components, from any of the ancestors, I could reach 11, but from 11, I couldn't go up the tree or reach any of the ancestors. So 11 has to be a representative. 11 has to be the highest vertex in its own strongly connected component. So at this point, I found a representative. And because I found a representative, I would just mark this 11 as a representative, and I remove it from the stack, okay? So 11 is now removed from the stack, and I say 11 was a representative. Okay, now from 11, I'm going to continue my DFS. So I'm going to mark 11 as black, go back to 10, and try to now continue my DFS. Now from 10, I see that I can go to 7, but 7 is before 10 on the stack, okay? So now I'm marking 10 as black, but I'm not removing 10 from the stack because it could reach something to the left of it or before itself on the stack. So 10 remains on the stack. Now, continuing my DFS, I go to 9. From 9, I see that I cannot go anywhere new, so I mark 9 as black as well. 9 has an edge to 10, right? But 10 had an edge to 7. So here's the thing. If I keep track of how much can I go back in my stack. So let's say that next to every vertex, I write what is the leftmost vertex on the stack that I could reach if I started here. So if I started from 10, I could reach 7. 7 was the leftmost vertex on the stack that I could reach if I was at vertex 10. Now, if I'm at 9, from 9, I can go to 10. But 10 could reach 7. So 9 can also reach 7. So I would put 7 here as well. Okay. So again, this is not the same as vertex 9. So starting from vertex 9, I could reach something that was before 9 on the stack. I could reach 7. Right? So I will not pop 9 from the stack. I will let it be. Now I go to 7. From 7, I see that I have another edge to 8, which is like a new part of the graph that I haven't explored before. So let's say, I'm sorry for this way of writing it. So I'm going to 8. 8 gets added to the stack. And now from 8, again, I see that I can go to 11, but 11 is not on the stack at all at this point, right? So from 8, what is the leftmost point on the stack that I can reach, it's 8 itself. And 8 now becomes black. And at this point, I understand that 8 is also a representative, and it's basically its own strongly connected component, because it could not reach anything that was to the left of it on the stack, and all of its ancestors were to the left of it on the stack. So 8 is a representative, and now I remove 8 from the stack. So whenever I get a representative, I remove it from the stack. Okay, going back to 7. Now, finally, from 7, I cannot go anywhere new. But what can I reach on this stack? So I can reach 7 itself. I can go to 9, but 9 could only reach 7. I could go to 8, but 8 could only reach 8. In any case, I cannot reach anything that is to the left of 7 on the stack. So again, I have the exact same argument as before. I have the argument that 7 has to be a representative because all of its ancestors are on the stack. And I cannot reach anything on the stack which is to the left of 7. So I cannot reach any of its ancestors from 7. And if I cannot reach any of the ancestors from 7, then 7 must be the highest vertex of its own strongly connected component. So at this point, I say that 7 is a representative. Now, what are the vertices that are in the strongly connected component of 7? Well, I can just pop from my stack until I reach 7, and all of those vertices are the vertices in strongly connected components. So I have 9, 10, and 7. Now, why are those the vertices in this strongly connected component? Well, because first of all of them could reach 7, right? So the reason that I didn't pop 9 and 10 was that they could reach something to the left of themselves on the stack, which also means that they could reach one of their ancestors, right? So I knew for a fact that 9 and 10 were not representatives. But they cannot be in the same strongly connected component with something above 7. Why is that? Because if something is above 7 and 9 can reach it, then 7 could also reach it, but 7 could not reach anything above itself, right? So at this point, I know that I have the strongly connected component, which is represented by 7, and it actually includes 9 and 10. Okay, I'm going to continue. So at this point, I mark 7 as black. I'm continuing my DFS. I go to 5. Now, from vertex 5, is there anything new I can see? Well, no, because I can only go to 3 and 4, and I've seen both of them. But importantly, I see that I can go to 4. So 4 is to the left of 5 on the stack. So the leftmost point that I could reach was 4. So I will not pop 5 from the stack. I would say that 5 just becomes black. Now I go to 6. What is the leftmost point of the stack that I can reach from 6? Where from 6, I could go to 3, and 3 could also reach 4. So I can reach 4. From 6, I can also go to 5, and from 5, I could reach 4. So from 6, I can also reach 4. So again, the leftmost point of the stack that I can reach from 6 is not 6 itself. So this tells me that 6 cannot be possibly a representative of a strongly connected component. So I let 6 remain on the stack. Now, I mark 6 as black. I continue my DFS. I go back to vertex 4. Now, here's where something interesting happens. What is the leftmost point of the stack that I can reach from vertex 4? Well, it turns out it's just 4 itself, right? So now, again, 4 is a representative because it can only reach itself. It cannot reach anything to the left of it on the stack. And since it cannot reach anything to the left of it on the stack, and since all of its ancestors, in this case only 1, are to the left of it on the stack, it means that 4 cannot reach any of its ancestors, which is just the definition of being a representative, because it's the highest vertex in its own strongly connected component, so it cannot reach any of its ancestors. So now I found another one of my strongly connected components, which is basically this one. And I can just pop from my stack until I get to the vertex 4. And now I continue this. I go to vertex 1. Remember that vertex 2 could reach vertex 1, and that was the reason why we didn't remove 2. Now, from 1, can I reach something to the left of 1 on the stack? There is nothing to the left of 1 on the stack, so the answer is no. So the leftmost point of the stack that I can reach from 1 is 1 itself. And so this is also a representative, which means that this is also a strongly connected component, and I remove these vertices from the stack. So this is called Tarjan's algorithm for strongly connected components. It does one DFS, and it finds all of the strongly connected components in O(n + n). So remember, for every vertex, I'm just keeping track of the leftmost vertex that is reachable on the stack, and then I pop a vertex from the stack when it becomes black, if and only if the leftmost reachable part on the stack, the leftmost reachable vertex on the stack was this vertex itself. Okay, now let's prove that this is actually a correct algorithm. So first of all, when I'm not popping something from the stack, I've already proven this several times when I was doing the example. So when I have a vertex and I decide that I'm not going to pop it from the stack, what does this mean? This means that this vertex could reach something before itself on the stack. Okay, now this thing before itself, so let's say I'm doing this. Let's say as I was doing my DFS, I have a vertex V, it has a bunch of children in my DFS tree. I've seen all of these children, so they've all become black. I have my stack. I have V at some point, I have things before it, and now I've reached vertex V, and vertex V is gray right now. I'm at the point where I want to mark V as black. But when I mark V as black, I don't remove V. Now, based on my algorithm, the only case that I would not remove V is if V could reach something before itself on the stack. So let's say that V can reach something before itself. So let's call that U. Now, if U is an ancestor of V, if U was here, for example, then of course V is not a representative because U and V are in the same strongly connected component, because of course I can take the 3 edges from U to V, and then I'm just saying that from V I can also go to U. So the representative of this strongly connected component would be U or higher. It cannot be V, right? So that's the first case. But let's say U is not an ancestor of V. So for example, let's say V has a back edge to U. Sorry, V has a cross edge to U. So U is here, and then they have some ancestor like this, right? So U was reached from V using a combination of cross edges and back edges. It doesn't have to necessarily be just one cross edge. Now, here's the thing. In this case, U would already be black, right? Because remember, our cross edges only go to the left, and U would be marked black before I reach V. But the fact that U was still on the stack means that U itself was not a representative. So U could actually reach something above U. And the fact that that thing was also on the stack means that this thing that U could reach was actually one of the common ancestors of U and V. Which again means that from V I can go to U, to that common ancestor, back to V. So V is not the highest node in its own strongly connected components. Okay? So this shows part of the correctness of my algorithm. And this is the part where I say that if this vertex V could reach something before V on the stack, then V is definitely not a representative. And of course, that was the case when I didn't remove V from the stack either. Now, we had the opposite case as well, and we have to prove its correctness too. We said that if V cannot reach anything before itself on the stack, then V is definitely a representative. Well, this one is kind of easier to prove, because when I reach V, I know that all of the ancestors of V are still gray. But I add a vertex to the stack as soon as it becomes gray, and I only possibly remove it when it becomes black. When it becomes black, I may or may not remove it. So when I'm reaching vertex V and when I'm coloring V from gray to black, I know for a fact that all of its ancestors are on the stack. And of course, all of them are to the left of V. So if V could not reach anything to the left of itself, it means that V could not reach any of its ancestors, which is the same as saying that V is the highest vertex in its own strongly connected component, so V is a representative. So you see, this proves the correctness of Tarjan's algorithm. We will see how to code Tarjan's algorithms. I want to also show you something interesting, which is actually, this is a theorem in graph theory, and they have a very hard proof for it using induction. I'm going to give you a much easier proof using DFS. So this is going to show you how to use these algorithms to give proofs of mathematical facts. So remember the previous problem, like the one before strongly connected components that we talked about, was bipartiteness. So we said a graph is bipartite or two-colorable if and only if it does not have any odd cycles. That's very well known, and I hope that you remember it from previous courses. Now, what if instead of 2 colors, I have 3 colors? Now, it turns out 3 colorability is actually a very hard problem. It's an NP-hard problem. We will hopefully get to those later. So generally speaking, if I give you a graph G and I ask you, can you color this with 3 colors? That's a really hard problem. Okay, but I'm going to take a very special case. I'm going to say in the input, I'm going to give you an undirected graph G. And I'm going to additionally make sure that this graph does not have any even cycles. Okay, so I have an undirected graph G without even cycles. So I don't have a cycle with an even number of vertices. And as output, I want you to color this graph with 3 colors. So I want a 3 coloring of G. And of course, that means that I want you to assign one of 3 colors to every vertex in G, so that every edge connects vertices of different colors. Okay. Now, we can look at this algorithmically, but we can also look at it mathematically. And basically, the theorem that I'm asking you to prove is that any graph that does not have even cycles is 3 colorable. Right? Because if you can find an algorithm that successfully does this, then it's also a proof that any graph that does not have even cycles has a 3 coloring. Okay. So that's the theorem that we are trying to prove. A graph that has no even cycles is 3 colorable. Now, you can Google this later and you can find the hard proof by induction that mathematicians use, but we are computer scientists, so we're just going to give them an algorithm. And then we're going to say, I proved that my algorithm always works. And because my algorithm always succeeds, and because the output of my algorithm is a 3 coloring, then a 3 coloring exists. Okay, give me an algorithm. Give me an algorithm using DFS or BFS. So let's just use DFS. Let's say I just do DFS on my graph. Okay. And also I can assume that my graph is connected, because if it's not connected, just take each one of its connected components and color it separately, right? So I'm assuming that my graph is connected. I do a DFS, it gives me a DFS tree. So let's look at the DFS tree of G. Okay. I have this tree. Let's say this is my DFS tree. And remember that just like before, I have a division of edges now into 3 edges and back edges, because this is an undirected graph. Remember, we said that if you look at the DFS tree, where was it? Yeah, this one. We said that in the undirected case, every edge of the original graph is either an edge of the tree or it's a back edge. In the directed case, it was more complicated, but this is the undirected case. So I can only have 3 edges and back edges. Now, let's first consider the case where we're lucky and there are no back edges. If there are no back edges, I just have a tree, like my whole graph is a tree. I can color it with 2 colors. I don't even need 3 colors, right? I can start at the top. I can say use red for this one, and then for the next level, use blue, and then for the next level, use red again, and for the next level, use blue. So I colored it with 2 colors. I didn't even need to use my 3rd color. But of course, I'm not usually going to be that lucky. So I'm going to have some back edges. What happens if I have a back edge? So let's say I have a back edge like this. Is this okay? Can I have this back edge in my tree, in my graph? No, because this particular back edge is going up by 3 levels. So it's creating an even cycle. It's creating a cycle with 4 vertices in it. And my assumption was that my input doesn't have even cycles. Okay, now because my input doesn't have even cycles, whenever I have a back edge, it connects some vertex to one of its ancestors that is an even number of levels above. I can never have a back edge that goes up by an odd number of levels. Okay, so I will never have this kind of back edge. But of course, I can have this back edge, for example, right? Because this one is creating a triangle, it's creating a cycle with 3 vertices, and that's allowed. I can have odd cycles. Similarly, I can also have this kind of back edge, because it creates a cycle with 5 vertices. But now here's my question. Can I have both of them at the same time? No, because having both of them at the same time will create this cycle, which is an even cycle, right? So this shows that if I look at each one of my vertices, first of all, the back edges that go out, they can only go up by an odd number of levels. But secondly, I can have only at most 1 back edge from any particular vertex. Because if I have 2 different back edges from this vertex, I would just use those 2 back edges and the path in the tree between their endpoints. And that gives me an even cycle. Great. So look at this. Now I have my tree and I have a bunch of back edges, but I know that from every vertex, I have at most 1 back edge going out. From some vertices, maybe I have none, but I cannot have 2. I have at most 1 back edge going out of every vertex. Right. And now I want to color the whole graph with 3 colors. So I'm just going to start at the top of my tree, and I'm always going to use the first color that I can use. So I'm going to say, let's color this one with whatever my first color is. I'm assigning color 1 to the root. Now I go to the next level. I say, look at your parent. What is the color of your parent? Just pick a different color. If your parent is color 1, pick 2. Okay. Now, sometimes, for example, here, when I get to a vertex, well, its parent is already colored, but maybe this vertex also has a back edge. And I have to make sure that the color of this vertex is different from its parent, and it's also different from the color of the ancestor that is connected to it by the back edge. But I know that I have at most one back edge. So at most two of the colors are taken. The color of the parent and the color of whatever the other vertex on the other side of this package was. So I always have a third color to assign to this vertex. So let me just complete this. Let's say this was the package that I had here, and this was the package that I had here. This was the package that I had here, and I don't want this one. Okay, so I'm going to start from the top. I color this one with the first color. This one is connected to its parent. The parent has already colored one, so I'm going to color it too. This one is also connected to its parent, so color one is taken. I just color it too. Now I go to this one. It's connected to one vertex of color one and one vertex of color two, so I can use my third color here. Now I go to this one. It's only connected to a vertex of color two, so I can use color one here. I go to this one. It's connected to both colors, 1 and 2 before, so I can use color 3 here. And I just continue like this. This is connected, and so this vertex is connected to a vertex of color 3, so I can color it 2, let's say. This one is connected to both 1 and 2, so I color it 3. This one is only colored to 3, so I color it 1. This one is only connected to 2, so I color it 1. I can always succeed because whenever I'm coloring a vertex, it's only connected to at most 2 vertices that are already colored. So I always have a third color to assign to this vertex. And so this is, again, a linear time algorithm. This is O(n plus m. And it always succeeds. And because my algorithm always succeeds, I have the theorem. I know that any graph that has no even cycles can be colored with 3 colors, because I just told you how to do it. Okay. Great. So now we're going to move on and we're going to see something else. And this other thing is Dijkstra's algorithm. So remember that one of the problems we considered before was the problem of shortest path or distance. So I give you 2 vertices, u and v, in a graph, and I ask you what is the distance from u to v. And we said we can just solve this using a BFS. We do a BFS from u, and we just see how many levels it takes before we get to vertex v. BFS calculate the distance. But now suppose that my graph is weighted. So I'm going to take the graph that I had before, and I'm going to do this on an undirected graph, but it also works on directed graphs. So for the purpose of this algorithm, I don't care if my graph is directed or undirected, and you'll see why. But let's say this is my graph. But previously, I didn't have any weights on the edges. I was just assuming that the length of every edge is exactly 1. And then the distance from one vertex to another vertex was just the number of edges in the shortest path. But now I'm going to say that my edges have different lengths or different widths or whatever, different weights. There are some numbers on them, right? So I'm going to say, for example, this one is 1, this one is maybe 0, this one is 2, and let's say this one is also 0, this one is also 0, this one is 3, this one is 7, this one is 1, this one is 2. Okay. You can think of this as like the cost of traversing that edge. So now when I'm asking you for the shortest path from a vertex to another vertex, I'm not asking for the path that uses the smallest number of edges. I'm asking for the path that has the smallest total cost. Okay. So for example, suppose that I tell you what is the shortest path or what is the distance from 1 to 3. Now, I can just take this edge, and that would have a cost of 2. Or I can go to 2, then 4, then to 3, and my total cost would be 1. So I would prefer this one. I would prefer to pay a cost of 1. So that's how I'm defining my shortest path now, or my distance. So my distance is the smallest cost that I have to pay in order to go from U to V. Okay. And I want to calculate these distances. So my input is a weighted graph G. And by weighted, I mean that I have a cost or a weight or a length on each one of my edges. So I have a cost function C that to every edge assigns some cost. And I'm assuming that my cost cannot be negative. Okay, so it assigns some costs. And I'm also giving you, let's say, 2 vertices, U and V, vertices of G. And I'm asking you to output the distance from U to V. So the output should be the distance from U to V. And again, remember that the distance is the minimum total cost that I can pay in order to go from U to V. Now, why am I saying my costs are non-negative here? Because a lot of crazy things can happen if you can have negative costs, especially if you have a negative cycle. So imagine if I have, for example, a self loop from a vertex to itself with cost -1. I can just keep taking it, and then all of my costs will be minus infinity because I can make money basically by taking that road. So for now, we're just going to assume that our costs are not negative, but later on, we will talk about negative costs as well. Okay, so in this case, let's say that I give you vertices 1 and 7, for example, and I ask you, what is the distance from 1 to 7? Or I might also ask you, what is one of the shortest paths? So again, the shortest path is almost never unique. So whenever I ask you for a shortest path, I'm not asking you for all of them. I'm asking you for just one option that is optimal, right? So I'm asking you, I want to go from 1 to 7. What's the best way to go from 1 to 7? Well, I can do this, right? I can pay a cost of 1 to go to 2, then pay a cost of 0 to go to 5, and then pay a cost of 1 to go to 7. So the distance, it seems, is 2 if I don't have any better path. Okay. And then what is the cost of, or what is the distance of 1 and 6? What is the minimum cost of getting to vertex 6 if I start at vertex 1? Again, you can probably figure out that this is the best path, so it's 4. Okay. But again, this is not the shortest path in terms of the number of edges, because this path is using 4 edges, but I do have a path with 3 edges. But again, I'm always preferring the path that has the smallest total cost. And when I talk about the length of a path, I mean the total cost of the path. So I use all of these things interchangeably. Weight, cost, length, they're all the same. Okay. How would you do this? How would you calculate it? Well, here's a simple algorithm that Dijkstra came up with. It says, I'm going to start from my first vertex, whatever it was, my starting vertex U. In this case, it was 1. And I'm just going to try to find shortest path to the other vertices. And I'm going to try to finalize my shortest path to as many vertices as possible and as soon as possible. So here's the thing. If I start at vertex 1, first of all, the distance from 1 to 1 is 0. That's obvious, right? I can just stay where I am and not pay anything. Now, from 1, I have 2 edges. So if I have any non-empty path, I have to take one of these 2 edges. There is no other way. So this tells me that if I look at the edge with the smallest weight, if I look at the edge with weight 1, actually that's the shortest path to the next vertex. So the distance to 2, I'm going to just write the vertices here and the distance here. So I started by saying that the distance from 1 to itself is 0, But now I can immediately say that the distance to 2 is 1. And I can just do this saying that 2 is finalized. I'm sure that no matter what, I'm not going to find a better way of reaching 2. Because I know that when I start here, I have to either take this edge or this edge. If I take this edge, I've reached vertex 2 with cost 1. But if I take this other edge, I have already spent more than that cost. So it's never going to have a cost of less than 1. So I'm sure that this is definitely the shortest path to 2. Okay, great. And let me just put this edge in red as well. Now, here's the thing. I know that the distance to 2 is exactly 1. But what do I know about the other distances? I know that the distance to vertex 3 is at most 2. Because I have this edge that has length 2 or cost 2, and it goes to vertex 3. But I'm not sure that this is optimal, right? Because maybe there is a way of taking this other edge and going around the graph and coming back to vertex 3. And in this case, there is. I can just go like this, right? So at this point, the distance to vertex 3 is not finalized. All I have is an upper bound. I know that I can reach it with a cost of 2, but maybe I can reach it with a cost of less than 2. Okay. But additionally, because the distance to 2 is 1, I also know that the distance to 5 is at most 1. And the distance to 4 is also at most 1, right? Actually, maybe instead of a 0 here, let me put, I don't know, 1 here. So the distance to 2 is 1. So the distance to 5 is going to be at most 2. The distance to 2 plus the weight of the edge from 2 to 5. So I know that the distance to 5 is at most 2. And similarly, I know that the distance to 4 is at most 1. Right? Now, this is all the information that I have until this point. But among these vertices, which one can I say is finalized? Which distance am I sure will never change? The distance to 4, the smallest distance. Right? Why is that the case? Because you see, the distances to 1 and 2 were already finalized. I know what the correct answer was to them. So when I start at 1, I'm going to take a path. And this path, at some point, it's going to leave the finalized vertices. It's going to go to the other vertices, right? Now, I know that I can go to 4 and pay a cost of 1. Now, if this path doesn't go to 4 first, it goes, let's say, to 3. It's already paying a cost of 2. So it doesn't make sense to go to 3 and then try to go somewhere else in the graph and come back to 4, right? So the distance to 4 is now finalized. Generally speaking, I always know that the shortest distance is finalized. I cannot get a better alternative for my shortest distance ever. And again, this is because all of my costs are non-negative. If I had negative costs, I couldn't say this. But because I know that all of my costs are non-negative, I can now say that the distance to 4 is finalized. So this is finalized, and I know that the best path to 4 is from 2. But now that the distance to 4 is finalized, I can update the distances to the neighbors of 4. So I can get to 4 by a cost of 1, and then I can take this edge, and it would take me to 5 with a total cost of 4. But I have a better way of reaching 5, so I'm not going to update that, right? But from 4, I can also go to 3. And that would give me a cost that is equal to the distance to 4, which was 1, plus the cost of this edge from 4 to 3, which is 0. So now I found a path to vertex 3 with distance 1. So I update the distance to 3, and the distance to 3 is now at most 1. Okay? Now, again, among all the distances that are not finalized, I'm going to take the smallest one, and I'm going to say this is now, again, finalized for the same reason as before. So at this point, I'm sure that the distance to 3 is correct, and I can never find a path that is cheaper than 1 to get to 3. So this distance is finalized, and I add this there as well. Okay. Now I'm going to just continue like this. 3 doesn't really update any of the distances. So again, I take my smallest distance, which is 2 here, and I say this is finalized. So 5 is finalized, and this was the best path to 5. And then from 5, I can update the distances to 6 and 7. So I know that the distance to 6 is now at most 9, and the distance to 7 is now at most 3. Right? Now, again, I take the smallest one. I say this is finalized. So the distance to 7 is exactly 3. And I use that to update the estimation of distances for all the neighbors of 7. So I'm going to say from 7, I can go to 6. So it costs me 3 to get to 7. It costs me another 2 to get to 6. So the distance to 6 is at most 5. Right? And now at this point, the distance to 6 also gets finalized. So I know that the distance to 6 is exactly 5. Okay? So I found all of my distances. And not only I found all of my distances, of course, on this side, I was creating a tree. And this tree gives me all the shortest path that I was looking for. Right? So I connected every vertex to its parent, and its parent is basically the vertex that gave me the best alternative for reaching this one. Right? So I know that the best alternative for reaching 6 was to first reach 7 and then take the path, the edge from 7 to 6. So now if I want the shortest path to 6, I know that it ends with this edge. But then, of course, if I want the shortest path to 7, I know that it ends with this edge, and so on. So if I want the shortest path to 6, it's just the path in red in this tree. And that starts from 1 and goes like this to 6. So let's just see what our algorithm computed. Our algorithm for a fixed starting point, for the starting point 1, it computed the distances to all the other vertices. Okay. So this is what we call a single source algorithm, because I fixed one source and I'm finding the distance to every target, right? But not only I found the distances, I also found a tree which pretty much has the same properties as a BFS tree. Because remember, in the BFS tree, also the paths in the tree were the shortest path. It's the same here. It's a shortest path tree. So if I want the shortest path from 1 to 4, again, I just take the path in the tree. Okay. So this is called Dijkstra's algorithm. And I kind of told you why the algorithm is correct while I was explaining the algorithm. So I'm not going to do a separate proof, but I'm going to force you to read the proof. So I will put this on canvas. But you now understand how it works. So the idea was always just take the shortest distance that is not finalized, and you don't have any better alternative for reaching that vertex. So just finalize. Now the question is, how would you implement an algorithm like this? What are the data structures that you would use? And how are you going to basically get it to run in C++? And what is your runtime? So here's the thing. I had these vertices here, and I had the current distances to these vertices, and some of the distances were not finalized, right? So every time the operation that I wanted to do was to find the smallest non-finalized distance. Okay. So I have a bunch of elements. I'm always asking for the smallest one. What data structure does that? Heap. Right? So I can put all of these distances, the ones that are not finalized, in a heap. And every time when I want to ask which one is the closest one, which one has the smallest distance, I'm just going to ask for the smallest element in the heap. And let's say I have a min heap, so it's just the root of my heap. Okay. So that would allow me to basically find the closest vertex, find the vertex that I want to finalize in log n time. But how many times do I have to do this? How many times do I have to find the next vertex? N times, basically, n minus 1 to be precise, but it's almost n, because every time that I finalize the distance, I'm just done with one more vertex, and I have to do it for all the vertices. So I have n operations in which I'm asking for the smallest element of the heap and then removing that smallest element, right? So that's going to take n log n. But what are the other operations that I have? I also have this really pesky situation where I'm updating my distances, right? So it's not like I'm just inserting into my heap and then taking the minimum out. Sometimes I'm also updating the distances in the heap, right? So I'm taking some number in the heap and I'm updating it to something else. But I'm always only decreasing it, because the numbers are, again, the distances that I know until this point of the algorithm. So maybe for this particular vertex, I knew a path of cost 5 before, and now I know a new path of cost 4. So I have to reduce that 5 to a 4, right? But we've seen how we can do this kind of operation in a heap as well. We just change it, and then we bubble up. But each one of those changes is also going to take log n time. Now, how many times am I going to make changes? Well, you see, I make changes whenever I finalize a new vertex, and then I change the distances to all of its neighbors. So I make one change for every edge at most, right? So for example, when 5 was finalized, I went over all of the edges that were going out of 5, and I updated the distance to the other side, right? So for every edge, I'm doing one update. And of course, for every vertex, I'm also doing an insert at the very beginning. So the total number of heap operations that I'm doing is O(n plus m), but every heap operation also takes log n time. So my total runtime would be O(n plus m) times log n, if I implement it with a heap, right? And now, of course, normally m is much bigger than n, so I would just write m log n normally. So again, m is the number of edges and n is the number of vertices. But this is if I use a heap. What if I don't want to use a heap? I can just say I keep all of these distances in an array, and every time that I want to find the minimum distance, I just go over my array, right? If I do that, finding the minimum every time takes O(n) time. But I have to find the minimum how many times? N times. So finding the minimum is going to take n squared time. But what are the other operations that I had? The other operation I had was updating distances. But now, because it's just an array, updating a number in an array, that's constant time. And I'm doing that n plus m times, right? So it would just be n squared plus n plus m. And of course, n squared is more than n, so I'm just going to write n squared plus. So if I just implement it with an array, if I don't do any interesting thing, I don't say that I have a priority queue or I have a heap, I get this runtime, n squared plus m. Now, which one is better? It depends on your input, right? If I have a graph that has a ton of edges, if I have a graph that is almost complete, so if m is almost n squared, then this one would be n squared times log n, but this one would just be n squared. So this one would be better. But if I have a graph that has relatively fewer edges, let's say I have a graph where the number of edges is much less than n squared. I have a graph with, I don't know, let's say I have a tree, right? M is n minus 1. Then this one would be n log n, but this one would be n squared. So if you have a sparse graph, if you have a graph with few edges, this one is better. If you have a graph with a lot of edges, the number of edges is almost the number of vertices squared times some constant, then this one is better. Again, it's the same algorithm, just using different data structures. You get different runtimes, and you have to choose based on your particular problem which one you prefer. And yeah, we ran out of time. I'm going to code this and put a video on Canvas that shows you how to code it in C++. Okay, see you next week.